Okay, I'm back, and I brought Ecofish with me. Actually, this is still a picture of Ecofish. This is PowerPoint. In a moment, I'll cut away and show you the real thing in a Stella window. But before I do, I want to make a point, and the point is that the experiments that we are now simulating with Ecofish, the virtual experiments, were experiments that we once did with real fish, or tried to do with real fish. We didn't always succeed. And the thing that has made Ecofish a success, though, is the fact that when I started to put it together, I promised myself that I would make Ecofish do all the same experiments that the real fish had to do before, that we wouldn't cut any corners, that the same treatments would be applied, that I would find a way to simulate not just Ecofish's responses, but also the manipulation of treatments that was required in order to generate those responses. And I think I succeeded, and I think that's why Ecofish is, I think, a very good success. Okay, let's stop with PowerPoint now and go to Stella. So the first thing I'll have to do here is end my screen show and then bring back up Stella. And so there you see basically the same view that you saw before, except now I can move things around because this is a real live window using PowerPoint. This is I call this Ecofish with its scales on, whereas before you saw Ecofish with its scales off. This is the way the students normally see it. They see only the part of Ecofish that needs to be accessed, in this case the input-output sector for the enviroregulatory exercise. They see that part because just as in the case of real fish, you can't look inside. With Ecofish you actually could look inside, but you don't have to. The way it works is the students impose treatments on Ecofish. They observe Ecofish's responses, and then by analysis of those responses, they try to infer the biology that has gone on inside. We do a series of 6 laboratory exercises during any particular semester of biology of fishes. Each of the exercises normally takes us 2 weeks. The first week, we introduce the exercise and do the actual simulations that generate the data. And then in the following week, we get back together and process those data, do the analysis, and reach our conclusions, prepare graphics, tables, that sort of thing. The 6 exercises that we do, number 1 is stomach evacuation rate and maximum daily ration, and the sector that handles that is the sector down here, and naturally enough the mouth position. The second exercise is routine metabolism and respirometry, and this is the input-output sector for that exercise. The third one is toxicity bioassay, in which we investigate the lethal effects of copper and ammonia to Ecofish. The fourth exercise is heat transfer and body temperature and why ordinary fish are portilotherms and tunas aren't. Then the fifth exercise is the one that I want to demonstrate in this presentation. That's the enviroregulatory exercise. I'll have more to say about that in a moment. And then the final exercise, sort of the grand finale that puts everything together, is the growth exercise. A really important part of this system, though, isn't part of Ecofish, the fish. It is part of Ecofish, the model, and that's this sector up here, which contains all of the environmental information and the treatment manipulations. And you can see Ecofish is very well connected to its environment. So, with that bit of preface, I want to go back to the sector here, just upstream from the caudal peduncle. and let's have a look at what's inside it. So I will click there and then come down and hit the little plus sign, and that allows me to zoom in on my model so that I can get a better view of what's there. And I'll do it again so that you can get a better view. And it's still a little bit small. We'll try one more. And there, finally, we can see all of the stuff that we need to see. This is Lab 5, and Lab 5 actually has two subdivisions, one for temperature and one for dissolved oxygen. We're going to play with the temperature part of Lab 5. In this exercise, we simulate thermoregulatory behavior of ecofish in a one-dimensional, long, tubular temperature gradient, very similar to the one that we once used with real fish. This particular one is 10 meters long. We use very small fish. We can choose different weight classes. The nominal value that's set up when the model opens is the smallest weight class. Fish that have a mean weight of 2 grams. The weight of the fish is a stochastic variable. That is to say, when one runs the model, you get a fish drawn at random from a distribution that has this mean, in this case 2 grams, but with a normally distributed error, I think 0.05 grams in the case, or 0.5 grams, I guess, in the case of the 2 gram fish. So we got small fish in a very long tube, and the idea is that we've got in that tube heat exchangers in the floor, countercurrent heat exchangers, so that if we flow heated water or heated fluid in one direction and chilled fluid in the other direction through these titanium clad heat exchangers, we will generate a nice temperature gradient. Not as linear as we would always like, but still a nice extensive steep gradient. What we're going to do is simulate the movements of a single individual mean 2 gram weight ecofish in this gradient and plot its course in space and in temperature. Before I go on with that, just let me say that the other part of that exercise deals with ecofish vertically moving in a vertical gradient of dissolved oxygen concentration. By the way, it's really important to point out that ecofish is doing everything all the time. In other words, we are only focusing on behavioral and viral regulation now, but when we run the model, all of the other parts of the model are also running. And since the natural time step for some simulated processes like growth is much different from others like movements in a temperature gradient, we have to run the model at with different DTs, different differential times, different time steps. The behavioral and viral regulation model for temperature is set up to run with time steps of only 0.002 hours. That, I believe, is, let me think, that would be 7.2 seconds, I believe. So every 7.2 seconds, ecofish has a chance to turn around in this one-dimensional gradient and go the other direction, or it can continue going in the direction that it was going in the previous step. So that's the kind of behavior we're talking about, and we're going to follow the outcome or the resultant of that behavior. Well, let's just open it up and run it. Here are the main outputs of interest. Although students, when they run this, the students need to look at the tabular data. They always enjoy watching the graphical data more. And this is set up for a higher resolution display than the 600 by 800 display that I'm using for purposes of this recording. So I'm going to have to play with these two graphs a bit to scale them so that they'll both fit on the screen where we can see them both simultaneously. So I'm going to cut away for a minute while I do that. Okay, I got the two graphs side by side and then realized that they're going to be shrunk down so small that you're not going to be able to read the variable names if I do it that way. So I'm going to show you each of the two graphs independently, and then I'll go back and put them side by side again. But let me just explain that on the left-hand graph, what I've got on the y-axis is temperature from 15 degrees to 40 degrees. And on the x-axis, there will be time. Now, the time scale will not be 25 hours the way it's shown here. That is a holdover from the previous time when the model was run and saved. So that will change as soon as we execute the model. I was just thinking, if I'd been clever and was just a bit better producer, you get, a little bit strained being your own actor and director and stage manager and technician and lights guy and producer. What I would have done is I would have run this model one time off camera, so to speak, gotten my time scale straight, and then dynamited the contents of the graphs, and you would have never known the difference, right? You would have thought, well, it's the way it ought to be. But I'll just tell you the truth. Okay, so this time scale is going to change the first time we run it. In fact, it's going to go, let's look again. It's going to go from 2.22 hours to 5 hours at 0.002 hour intervals. So this graph is going to take a while to build. In other words, the model is going to take a while to run. Why, do you ask, am I starting at 2.22 hours? Well, it's because I want to start the fish in the middle of this 10-meter long tank, and I want to start the fish at the temperature to which it's acclimated, and I want to work with a 25-degree acclimated fish. And the way Ecofish operates, it assumes that the first value of the environmental variables are the values to which Ecofish is acclimated. Ecofish actually makes acclimatory responses, that is, physiological adjustments to changing temperature and to changing DO. 5 hours because that's about as many hours as we can squeeze in. The number of steps is limited in Stella to some maximum, finite maximum. I forget what it is, but that's not many more than that. So here we go. Minimum temperature in the tank, maximum temperature in the tank at every instant, and the tank temperature changes because the way we did this experiment in reality back in the good old days, we'd start off the tank with only a chilled flow of fluid running through the cold heat exchanger, nothing running through the hot one, and then we would gradually bring up the temperature of the hot flow and cause the tank to warm over time. The warm end would warm faster than the cold end, and that would cause a gradient to develop. And then when finally the gradient got to the point where the temperature to which the fish we were using as experimentals was acclimated, we'd drop it in the tank at that temperature and then follow the behavior. So that's why the simulation starts at 2.22 hours, because that's the time when the tank temperature reaches the right value. Just keep in mind three variables are going to be plotted here concurrently. Minimum temperature in the tank, temperature that the fish is at, which is guaranteed to be somewhere between the minimum temperature in the tank and the maximum temperature, and then the maximum temperature. Okay, that's what's on this axis. Now, I'm going to squeeze this one back small, maybe not that small, and open up the other where we can see it, because I want you to admire my handiwork. This is what is called a scatter plot in Stella. It's a plot of two variables against each other when the one on the x-axis is not time. Stella only does time series and scatter plots. This particular scatter plot is an interesting one, because what I managed to do was to arrange to plot the frequency distribution of the temperatures visited by Ecofish during a particular simulated experiment. So what you're going to see build here on the same temperature axis as on the other graph, 15 to 40 degrees, is the frequency with which EcoFish visits each of the temperatures on this axis. So let me squeeze this back in place and let's run the simulation. And by selecting this graph, it will overlap with that one, but there's not much here to see, so that'll work. Okay, everybody's with me now, right? You know what you're going to see over here. You're going to see a time series, and over here you're going to see a frequency distribution, a histogram almost, stacked up on the y-axis. So let me run the simulation. Remember, this is stochastic, so we'll never see quite the same thing 2 times in a row. Okay, let's analyze what we saw there, and what we saw was a beautiful result. Here is the tank at time 0. It looks like the minimum temperature in the tank at time 0 is 19.4. The maximum is 30.5. And sure enough, the temperature in the center of the tank where EcoFish is released is 25.0. That's the reason we started the experiment at 2.22 hours. Over the first couple hours, in fact up to 2.92 hours, the gradient is still forming. It finally reaches its maximum allowable extent, which is 20, a little over 20, looks like, to 35, and then we stop the gradient there. We don't let it get more extensive than that. So what you can imagine is that between the red line and the purple line there is a linear temperature gradient, equally steep over its whole extent. And so what did EcoFish do? Well, EcoFish came out of the chute, thermoregulated by going into slightly warmer water, and then leveled off, and thereafter it was a very good thermoregulating fish. It maintained its temperature, its immediate environmental temperature right around its body, right at about 27 degrees. And over here we see the evidence of that. There's the frequency distribution that's accumulated. And when I run this thing again, of course, EcoFish will probably do one of its rare flying leaps of death. EcoFish actually dies, by the way. We keep track of whether or not EcoFish succeeds by monitoring the accumulated heat and cold doses. EcoFish suffers lethal temperature death like a real fish would. And so if EcoFish is careless, EcoFish dies. But EcoFish ended this particular trial with no heat dose, no cold dose, and of course it had no death time because it didn't die. This is the spatial position of EcoFish at the end of the trial at 2.58 meters. This is the ambient temperature at the end of the trial. That's the average temperature experienced by EcoFish. That's the temperature EcoFish was acclimated to at the end of the trial. Here's its, and frankly I forget exactly what the distinction is between the gross swimming speed and body lengths per second and body lengths per second. I couldn't tell you what that is. But let's go back and run it. By the way, that particular fish was 2.1 grams, and actually for a redfish that would be 60 millimeters total length. So let's open the graphs back up again and try again. That was probably just a fluke, right? Probably EcoFish could never do that again. Let's see if it can do it again. It won't do exactly the same thing. See, it sure enough did bump its nose on the cold end of the tank, just like real fish are wont to do from time to time, but it recovered. Here's the evidence of that experience down here. But notice that it ended the trial still with no heat and no cold dose. So any dose it accumulated, it managed to dissipate. And that's part of what's built into EcoFish, a natural recovery process. We can save ourselves trouble. After this one, I will go and do run using the run controller. You may notice that the distribution of ecofish doesn't start to build until we have established a constant gradient. I think it's at 3 hours. When time is greater than 3, then this distribution accumulates, and before that it doesn't. If you watch this time, you'll see that it's that the frequency distribution doesn't start to form until we have 3 hours on the clock. There it started. So we could just sit here and run trial after trial after trial and watch ecofish thermoregulate. It may be occurring to you, how does ecofish thermoregulate? I know people who have watched real fish thermoregulate, published papers on it, and I don't think that question ever crossed their minds, but it crossed my mind. And I don't know how real fish thermoregulate. I've got some hypotheses, and one of them is invoked in ecofish. The hypothesis in ecofish is ecofish increases the probability of changing direction whenever there is a reduction in metabolic scope for growth over the last time step. That's a pretty simple statement of the rule. There's an even simpler way to state it, and that is ecofish increases its rate of turning whenever it detects things are getting worse. And things getting worse means the convergence of all of environment is moving towards making the last move ecofish made one that tends to lessen the available metabolic scope. And ecofish doesn't like that. Ecofish doesn't care, but there's a probability distribution that cares. And so the likelihood of ecofish changing direction increases whenever ecofish starts moving into a situation that decreases its metabolic scope. It may have occurred to you that this is kind of handy because that means ecofish doesn't care what it's regulating. It's environmental regulating. It's not regulating temperature. It's not regulating DO. It's regulating the joint distribution of all of those variables and how they affect metabolic scope. Let me show you a particularly interesting feature that really, I guess, emphasizes that last point. Some of you may have noticed that there are these strange-looking icons down here labeled bug time and Q time. Well, Q time is just the time when the temperature-frequency distribution turns on. That's 3 hours, so that's not anything strange. But bug time is quite strange. Bug time is the time when bugbear appears. And right now, bugbear is appearing at 10 hours, and the experiment only runs to 5 hours, so bugbear never comes out. Let's change that to what do you think? 3 hours, huh? Or no, let's make it 4 hours. What is bugbear? Bugbear is something that disturbs ecofish. Whenever ecofish gets close to bugbear, ecofish's routine metabolic rate increases due to anxiety. When ecofish's routine metabolic rate increases, that is a deduction from metabolic scope for growth. And so getting close, moving towards bugbear means that things are getting worse because my metabolic scope for growth is deteriorating, and so the probability of a turn is increased. There's another thing here that you may have noticed called strangeness, and strangeness is a wearing away of that effect, an attenuation of bugbear's negative impact on metabolism. The idea is that if bugbear turns out to be innocuous, then as ecofish visits bugbear more and more, it finally gets the idea that bugbear is not to be feared, and therefore the effect on metabolic rate goes away. So let's late at 4 hours. I'm going to go back and make that. Let's make it 3 hours. I want to have plenty of time for bugbear to have its effect. Yeah, we'll open up the graphs, and here we go. And let's see what happens. So where is bugbear? I didn't tell you that. Where bugbear is right here where ecofish wants to be. I think at 4 meters from the cold end of the tank, which happens to be the place where 27 or so degrees occurs. And if you look at the distribution, you can see that it's one-sided. That is, Ecofish is on the cold side of bugbear and dares not go closer. So let's try it again. Ecofish is on the warm, but Ecofish crossed over. Look at this bimodal distribution in Ecofish's density or frequency. Ecofish, by chance, made the step across. And so what's going on here? What's going on here is what I said before. It's the joint distribution of environment that is having its effect on the metabolic scope for growth of Ecofish. And the presence of bugbear takes away from metabolic scope because it increases routine metabolism due to anxiety. So what's happening here is that Ecofish is sort of trapped between a depression in the quality of available habitat right here due to bugbear's presence, and a depression in the quality of habitat over here due to the fact that temperature's too high, and over here because temperature's too low. So, by the way, strangeness only went down to 95. When strangeness goes to 0, then bugbear is no longer has no effect. But it takes many visits for that to happen. We could do longer simulations and observe this time strangeness went to 0.77. So Ecofish was getting over bugbear when the simulation ended. Okay, I think probably we've had enough of that. So what I'm going to do now is stop this part of the program and wrap it up. Okay, well that's what happens on the first week in the 2-week series. We talk about Ecofish, the particular version of Ecofish being used that week. We talk about the biology involved in the subject that we're exploring in the lab. In this case, we'd be talking about the mechanisms of thermoregulation, effects of acclimation on thermoregulation, that sort of thing, on preferred temperature. But that gives me the end that I need to talk about the other tools of 417 that I haven't mentioned except perhaps in passing. You know, here's the Ecofish as you just saw him with this enviroregulatory input-output sector open. During the first week in our 2-week sequence, we execute an exercise that's laid out in the handout that the students receive. This is a detailed handout, step by step, what to do, when to do it, what data to record. I pointed out that in this input-output sector that we were just looking at, there is a table, and actually it's the table that produces the data that are carried forward from the week of simulation to the week of analysis. What we do is cut the data from the Stella tables and then paste those data into an Excel spreadsheet and then carry out a sequence of instructions and make interpretive graphs like this one, graphing I think the preferred temperature or the temperature at which Ecofish occurred most frequently against the acclimation temperature of Ecofish. And in this particular case, you won't be able to see it, but I know it's there. We're graphing actually median and interquartile ranges of temperature for the sample of fish run by an entire 417 class. So if I got a dozen students, all of them are asked to simulate only one trial with an Ecofish acclimated to 20, one trial with an Ecofish acclimated to 24, one with, and so forth. And that produces a dozen or so values. Once they've analyzed their distribution, they come up with the preferred temperature for their fish. And we then analyze that distribution for median and interquartile range, and that's what's plotted. So we get the experience of dealing with sample size problems and outliers, these kinds of issues. And all of this is recorded using Camtasia, which is the software I'm using to produce this presentation. Everything that's done in 417, both in lecture and in lab, is saved in digital form to a Camtasia file. Those Camtasia files sometimes are produced in advance of the event, in which case the individual students will access Camtasia by downloading them from my server using an FTP program like this one. And then the individual student will put on a set of headphones and run or play the Camtasia file in one window while actually processing his or her own data set in another window. That way everybody works at his or her own pace. People can backtrack, they can fast forward, they can see what's coming to make sure they don't mess up now. They can check to make sure I didn't mess up in the future in my file. It's not nearly as much fun to do it this way, the way I'm doing it in this presentation, basically talking to myself. It takes some practice to do that. It's a lot more fun to talk to living, breathing students. So I don't really like the idea of distance education where I don't have any local audience at all. But it's a good way to compromise is to have some local students that you're talking to, and then the distant students are getting the benefit from the animated discussion that often occurs. So that's the way Biology of Fishes 417 works at Texas A&M, and I would welcome any feedback.